Hello, everybody. I cannot hear anything. Maybe it's my fault, but maybe not.
I hear everything.
Oh, now I can hear you. Oh, okay. Thank you.
How about now?
Yes.
Sorry.
Okay, I guess we can go ahead. So first of all, thanks so much for having me here. I know how painful it was to be able to have me visit for a few days. So this talk will be about AGN feedback, specifically in the context of the high redshift quasars. And I'll really be talking about quite high redshift. So I'll be showing a lot of results at redshift 6. So this is when the universe was less than 1 gig a year of age. Before I give you even an outline of what I'm going to talk about, I just want to give a sort of brief recap, especially for people who haven't been doing research for a long time, about sort of some of the basic concepts I'll be talking about. So the main observation, the guide to all this research, is that as far as we can tell, every galaxy, especially, and this is particularly true of massive galaxies, appears to have in its center a supermassive black hole. So the best example of this is, of course, the Milky Way, but this also seems to be true whenever we look at the nuclei of neighboring galaxies. And what has come as a surprise is that, strangely, these black holes seem to know about the properties of the host galaxies. And this is shown in different ways via a number of scaling relations that link the mass of supermassive black holes to properties of the host galaxy. So in this case, I'm showing you just an example of the relation between the black hole mass, and I guess I should use the mouse so people who are remote can see me, or maybe not. So I show you on the y-axis just the mass of the black hole, on the x-axis the mass of the stellar bulge at the center of the galaxy, and you can see that these two quantities are relatively tightly related. There's others, there's the luminosity, there's the velocity dispersion, etc. And this is strange because the scale difference between a supermassive black hole, even though it's very massive, it can be, as you can see, all the way to even 10 to the 10 solar masses, but the scale difference between a black hole and its host galaxy is enormous. It's actually the same, more or less, as comparing a ping pong ball with the planet Earth. Roughly depends a bit on which scale we choose. So the two scales I've written up there are on the one hand, the scale over which the black hole is able to influence gravity, and this then depends, of course, on how quickly the stars are moving. And then the second scale I've written there is the scale of the last innermost stable orbit in a non-rotating black hole. And if you compare that to the typical size of a galaxy, you get a dynamic range of something like 9 or 10 orders of magnitude. So it's strange that these two things are connected. And they hint, or they've hinted at, perhaps a common growing mechanism, so that the same thing that makes a galaxy grow also makes a black hole grow. But there have also been ideas that this suggests somehow that the black hole is influencing the galaxy, that it's stopping at any given black hole mass, the stellar mass to grow above a certain value. So that's one of the ideas that this observation can hint at. And of course, even though a black hole can be passive today, it must have grown somehow, and it must have grown in the past. And the main explanation, the sort of prevalent explanation of how these black holes grow, is that they swallow up material through gravitational accretion. So gas falls in and adds mass to the black hole. If you look at equations, for example, general relativity, and you estimate what's the binding energy that some test particle gains as it's accreted to the black hole, it's actually enormous. It can be something like 10% of the rest mass energy. So if this energy is then radiated away, and this we think happens through an accretion disk, which dissipates the kinetic energy that you generate as stuff falls into the black hole, then this phenomenon can kind of counterintuitively produce a very bright object. And this sometimes is confusing because people say, well, shouldn't a black hole be black? Yeah, of course, the black hole is black and is invisible, but the stuff that is falling into the black hole can be very bright. Okay, so if you just take typical values for how much of this rest mass you radiate away, a typical black hole mass, and something called the Eddington ratio, I'll explain in a second, actually the kinds of luminosities you're able to generate can even exceed the total luminosity of an entire galaxy. Here's an example I really like because it shows in the central quasar, which is at a distance of 9 billion light years away. And this thing here is an elliptical galaxy, which is closer to the Milky Way than this quasar. It's at 7 billion light years away. So there's a 2 billion light years separating these two objects. And that one is a star in our own galaxy. So the luminosities can be quite extreme. And of course, this energy does not necessarily have to be liberated in radiation. There's also other ways. One way in which we think this happens is through the formation of relativistic jets that carry this energy in mechanical form. So I'll, even in this talk, not even say much about jets, but I'll be talking about another way in which this energy can be released. This is via more spherical kinds of winds that we think are produced in the accretion disk. It's important to know that this radiation can come out in different ways. So here, just a few more quantities, and I mention these because I'll be talking about them. We sometimes forget that this is sort of not necessarily obvious if you're encountering it for the first few times. So I've already defined the accretion power. There's also a concept which is interesting as a reference. It's called the Eddington luminosity. This is the luminosity at which an AGN, an active galactic nucleus, or in other words, an rapidly accreting black hole, is able to balance its own gravitational force through radiation pressure. So you have a test particle, it wants to fall into the black hole because of its gravitational potential, but then this black hole is accreting, producing a lot of radiation. This radiation generates a pressure. This balance is called the Eddington limit. And you can see the kind of typical value. So you now understand what the Eddington ratio is. That's just how, for a given AGN, what is the fraction of the Eddington limit it's accreting at. So that's what I mean by Eddington ratio. And then finally, I can just plug this equation into the first one and derive what people sometimes call the Eddington accretion rate. This is the rate at which a black hole is growing if it's shining at the Eddington limit. And you can see that to do that, for example, for a 10 to the 8 solar mass black hole, it must be eating about 1 or 2 suns every year. Okay, so these are just some jargon that I'll be using liberally throughout this talk. And now it should get a bit more interesting. What's been a very big puzzle for quite a long time, and it keeps getting more puzzling every time people find a new most distant quasar, is that these supermassive black holes appear to exist already from the first gigayear of the universe. So the most distant one has a redshift of about 7.6. That's roughly 700 mega years after the Big Bang, or in other words, a few percent of the current age of the universe. And we think the masses, so these are then derived through methods which are obviously only very approximate, but for example, the width of emission lines. So we can derive some estimate for the masses, and we think they are something like 10 to the 8 or even 10 to the 9 solar masses, a redshift 7.5. And to understand why this is a real puzzle, I'm showing you this plot that shows an exercise that is people repeat almost every time they find a new quasar, a high redshift. So you guess what its mass history must have been if it was continuously growing at this Eddington limit. Okay, and then you get these smooth curves. And what that tells you is that if that's been going on, then these things must already have been 10 to the 4 solar masses, a redshift of 30. So you must have something at very high redshift that just forms these seed black holes very efficiently, very quickly. And we have some ideas as to how that may happen, but they are somewhat exotic. Of course, there's another way. You can maybe start with a smaller seed black hole, okay, even consistent with the remnants of the first generation of stars. But that, if you do that, then you cannot just follow this smooth curve. You actually need to grow at a faster rate than is allowed by this curve. And that means you need to exceed the Eddington limit. So that's called the super Eddington accretion. There's actually no physical reason why that shouldn't happen. Of course, the Eddington limit I showed in the previous slide is a spherically symmetric model. If you have non-spherical symmetry, you can exceed the Eddington limit. But actually, no matter what you do, you're stuck with a problem. And this is the problem. So either the supermassive black hole need to constantly accrete at the Eddington accretion limit, or you must exceed this several times during its growth period. And no matter what the answer is, if it's 1 or 2, you will need to explain where in the universe is that actually possible. Remember, we're crossing a range of scales of more than 10 orders of magnitude, 9, 10 orders of magnitude. And this tells you either 1 or 2 require this to be extremely efficient and to happen very fast in the early universe. So that's the first part of this talk is I actually will only spend 4 minutes on that because it's kind of old work now, but it sets the stage of the rest of the talk. So the first part is really, what is the kind of cosmological site that makes possible such rapid black hole growth? And then the second part will be dedicated to something called AGN feedback. As I mentioned, as you accrete gas, you can liberate large amounts of energy. Now, you can also calculate how much, what is the typical total energy released by a typical supermassive black hole. So that's just mc squared, m is the mass of the black hole, times some average radiative efficiency, how much of that rest mass you've radiated away. And then it's interesting to compare this with other properties of the galaxy. So the one in the middle, for example, shows the binding energy of the galaxy, the gravitational binding energy, which you can just get from the stellar mass and the stellar velocity dispersion. You can then take the third equation I have there on the right. That comes from that first plot I showed in the first slide that shows that the black hole mass is correlated with the stellar mass. You can put it all together in that equation that shows you that just a typical supermassive black hole over its lifetime has released about 100 to 1,000 times the binding energy of its host galaxy. So it can blow up its galaxy about 100 to 1,000 times. So this energy is another way of showing that this energy is really extreme. The problem, and this is the second problem that this talk will address, is how much of that energy do you actually use? So how much of that available reservoir is transferred to the galaxy, into the gas, and allows the AGN to actually impact the galaxy. And that, of course, then depends on the physical process. It depends on complicated things like the interstellar medium structure at redshift 5 or 6 or whatever. So really difficult problem. But and of course, it means you have to do all this. You have to be able to calculate these two things combined somehow, both the physics of the AGN and a realistic interstellar medium in a galaxy of redshift 6. Okay, so that will be the second part of the talk. I just want to show, before telling you what the third part will be about, that there is some growing, there is really growing evidence, especially in the last 10 years, that AGN really are impacting the environment. So observational evidence, I mean. So one of the main ways is that, just think, if the AGN heats its surroundings, it creates a high pressure region. This region expands and then it blows out gas. So this is what you call a galactic outflow. And we see these in systems that have bright AGN in the center. So this, for example, shows a biconical outflow emanating from a bright quasar. I think it was, I don't know what redshift this was now, but we see this even in different wavelengths, which is telling you that there's different phases in these outflows. So for example, this shows optical emission that tells you that there is gas at 10 to the 4 Kelvin roughly. That one shows you X-ray emission that tells you that there's also a much hotter phase tracing these large scale outflows. And then continuously people find new ways of detecting outflows and measuring them at higher precision. The plot on the right shows you yet another phase of outflows. It's actually the molecular phase. So the temperatures of 100 Kelvin or so. And it shows that the relation between, say, the mass outflow rate in these outflows to the AGN luminosity is very messy. So we don't really understand it, where this comes from, or if there's any relation at all. But there's some hope that there's something interesting is going on. So if you look, for example, the blue diamonds, they seem to show that there may be an envelope that does show some kind of correlation between the properties of outflows and the AGN luminosity in the center that would indeed suggest that the AGN are responsible for driving these outflows. So can we explain, is part of the talk is, can we explain these kinds of observations? And then the final slide before I move on is just to show you, and I tried to find a convincing way of doing this, that actually without AGN feedback, this AGN feedback is this deposition of energy by AGN. So without this process, we actually don't know how to explain the observed evolution of massive galaxies. And everything goes wrong, actually. And these plots show you results from different numerical simulations where people try to essentially model galaxy evolution in a supercomputer, solving the hydroid equations for the gas fluid, et cetera, et cetera. And it just shows you how different things can be if AGN are switched on and switched off. So if, for example, we see that a lot of massive galaxies locally are red and spheroidal, but that's what it would look like in the simulation if AGN was not driving this feedback mechanism. We also see that the star formation becomes inefficient as galaxies become massive. So galaxies struggle to form stars the more massive they become. But actually, the plot there in the middle tells you that if AGN did not operate in these simulations, so these are the colored plot symbols, you would form too many stars in these galaxies. And the list sort of goes on. Here is, for example, the X-ray luminosity of galactic halos versus the velocity dispersion, I think, of the galaxies. When you have AGN, you get much closer to the observation constraints than when you don't. Properties of the stellar populations in the galaxies, of the CGM, etc. And all these are different codes, different groups, different. I always say errors and bugs in the codes because they all have them, but they all reach this conclusion that you really need these AGN, or else we don't know how to explain massive galaxies, essentially. Yeah, that's just what I said. And then the final part of this talk, this just maybe comes across as if it's out of the blue, but it really is showing you that we can actually begin to probe both the quasar environments in these first supermassive black holes, and also the AGN feedback I've just been describing. And there's several ways in which this can be done, and people are still trying to understand how exactly you can test these theoretical models. But I just want to show you one example. I only have time to show you one example. of how we start looking for the emission of cold gas in the surroundings of the first supermassive black holes. This cold gas, of course, tells you something about the environment of these supermassive black holes, but also about the way in which the AGN has influenced its environment. So and I'll show you whether we can reproduce these observations or not, and how much they actually confirm or reject the theoretical explanations we have. So that'll be the third part of the talk. Okay, so I hope to spend 5 minutes in the first part and then about 15 minutes in each of these. And I'll stop in between each part, because if you really have a question and nothing is making sense, I think it's better that you ask sooner rather than suffer in silence until the end of the talk. Okay. So the first part of the talk is about the cosmic sites of the first quasars. So one thing I didn't say is that these systems are actually incredibly rare. Even though we see them at redshift 6 and 7, their number density is about 1 in a gigaparsec cube. So this is very low. And this means if you want to simulate this in a computer that follows, say, a kind of virtual mock universe, a virtual cosmologically representative volume of the universe, you would need to simulate a huge cosmological box. And you can do that, but you cannot do it at high resolution. So you can have a huge box, but then you're not going to resolve galaxies. And this is a bit of a dilemma. You can either really resolve galaxies very well, but then you have a small box, or you have a huge box and you get a lot of environments, but you get one particle to represent a galaxy. So one way to go around this problem is what's called the zoom-in technique, through which you select different regions of a big cosmological volume. In this case, it's a huge volume called the Millennium simulation. And what you do is you choose different regions, and then you simulate only these at high resolution. So that means that every time you simulate the whole box, but most of it will be populated by very low resolution elements. But the galaxy itself, you can then treat with as high resolution as possible. And to understand this growth of black holes in the high redshift universe, what we did was we've taken about 18 regions of this box. We've chosen these to essentially sample all the extremes of the cosmological environments at redshift 6. So you've taken, for example, 6 just random regions, the 6 most massive dark matter halos, and 6 halos somewhere in between. And then what we did was, and I will be explaining this a bit later, so don't worry, we just applied the sort of standard physical processes that people invoke for galaxy formation. So that will be some treatment for how gas cools. So the gas falls into a halo, it's shock heated, so it's hot. It's only after it cools down that it can sink to the center of the halo and form a galaxy. You then have a model for star formation and for what supernovae do once they blow up. You then have to model black hole growth. In this case, we don't believe in Bondi-Hoyle necessarily. We just did it because that's sort of the standard thing. And what allowed us to check whether the models people use, they do a good job at growing black holes, whether they would also work at redshift 6. And then this AGN feedback I've already described here, a very sort of approximate crude model where actually all the AGN is doing is heating the surroundings at a rate that is proportional to the bolometric luminosity of the AGN. And the kind of resolution we get in these galaxies is about 80 parsec. So if we didn't do that, the zoom-in technique would resolve maybe 5 kiloparsec or so. So it's really making a huge difference. Okay, so what happens? So these are 6 average regions. And what you can see is what's called a cosmic web, but at redshift 6. So it's still in its early days. It's not very clear. You see a little bit the slightly overdense filaments where galaxies form. And then you see in blue the voids, but actually there's not much structure there. And maybe some of you have already noticed also these black circles, they represent the location of black holes in the simulation of supermassive black holes. And they're very small because the plotting routine scales the size of the symbol by the black hole mass. So these are all low mass black holes. By low mass, I mean actually 10 to the 5. So masses are really a bit massive, but they're 4 orders of magnitude lower than the black holes we think are powering the quasars redshift 6. So in these average regions, so random regions of the universe, roughly at the background density on large scales, we don't form black holes using these standard models. If we go then instead to the 6 most massive dark matter halos of redshift 6, this happens. So the masses of these halos are about 5 times more massive than the Milky Way, but already redshift 6. So these are very extreme regions. They trace high sigma peaks of the cosmological density field in the young universe. But what you find is that, first of all, they look completely different. So there's certainly a lot of structure, and this structure takes the form of this complicated network of dense filaments that sort of intersects in some massive galaxy at the center. And in the center, you see these big circles that do indeed represent black holes with masses of 10 to the 8 to 10 to the 9 solar masses. So long story short, these models are able to reproduce very rapid black hole growth only if you go to these extreme systems that look completely different from an average galaxy redshift 6. And one of the predictions these models make, which I think has been untested until maybe last year, is that there should be a lot of this cold gas network. And that is why we then do the Lyman alpha observations, because we want to see if we can detect it and test these predictions. Okay, I could then go on and show you mass growth rates, etc. That's all in the 35-page paper you can look at from 2014. But I'll just move on to show you just a visualization of one of these halos. You will see 2 different colors, and this is it's an old video, so don't judge me for the quality. But you see 2 different colors. The blue is showing you gas which falls into the black hole. Red shows gas that is being ejected or has a positive radial velocity and is flowing out of the black hole. And you see the redshift there on the top left, and that just shows you first how this network of cold filaments is forming. These filaments are actually incredibly radial, as if they know exactly that they have to fall into the central galaxy. They start powering black hole growth. This then heats the surrounding gas, and starts driving these hot bubbles, which are potentially similar to those outflows I mentioned a bit in the introduction. What is already clear, and this is really something that I'll be coming back to, is that these hot outflows are not completely destroying the cold gas and preventing all the inflows and putting an end to the evolution of these galaxies as sometimes we hope you would. What happens instead is that you temporarily suppress the black hole growth because there's an outflow coming out, but then the inflow just comes in. It's very narrow, has a very small working surface, and it's actually very difficult for the outflows to push out this cold gas. And this means that these AGN feedback has some kind of fundamental limitation, which is the fact that it takes parts of this resistance and struggles to actually clear out all the gas. So any kind of immediate effect, at least in this kind of system, would probably be short-lived. You maybe suppress that formation, but you wait a few mega years and then it starts again because more gas is falling in. So I can maybe pause now and ask, nice, if there is any questions so far before I move to the next part.
Yeah, very good. I was wondering, there are black hole mergers during the gas.
Yeah.
And how those are important in building up the mass of the course.
Yeah, so as you saw, there were lots of these black circles. So there's one thing about these massive halos is not just that they have more massive black holes, but they have a larger number. And there is in the simulation a treatment to account for how they merge. As you may know, this is an unsolved problem, actually, how you get black holes to merge. And what these simulations, and that's also typical of models, these kinds of models assume, is that when they get close enough, you just merge them. So that's in. In terms of contributing, so the mass growth is completely dominated by accretion, but at very early stages, in the very high redshift, the mergers actually do play a role. So you see some jumps in the mass assembly history, which are sensitive to the merging and also then to the seeding of these black holes, how massive they are, how many they are. So I think that does play a role, particularly at higher redshift. Okay, yeah.
Is the feedback isotropic in that, right?
Yes, yeah, and that's actually a good point. So even though we see these
bubble is created by the cold gases.
Yes, yeah. So this the energy that the AGN is depositing is completely isotropic, but as you can see, the outflows aren't, and that's because they take parts of these resistance. They sort of collimated by the ambient disk, in fact, that sort of makes them go biconical. I'll show another example of that, and an even clearer one. Yeah.
These outflows are like energy driven, or
These are energy driven. Yes.
so you put okay.
In some very qualitative sense, in the sense that they are driven by thermal pressure.
Okay.
But whether they really approximate an analytic energy-driven solution is very questionable. I'll show you a model that I think does that.
Okay.
Yeah. Okay, so I just move on. If there's more questions, keep them. To the second part is really the bigger one and the most sort of intimidating one. So here it is. So I mentioned jets and radiation in the first part in the introduction, but actually what I'll talk about is another way the AGN have to release energy. This is in the form of very fast winds. So we think they're driven close to the accretion disk, so at scales of hundreds spatial radii, very close to the black hole. And actually, there's evidence, observational evidence, and Bologna, I mean, has played an important role in detecting these. So here we often see them as blue shifted absorption lines in the X-rays, and they could be so extreme as to have speeds which exceed 0.1 times the speed of light. In terms of how much energy they carry from the AGN, we think it's on the order of a few percent. 5% is the number people aim at, but it could be 1%, 10%. But this is a really small scales, and you could then give a colloquium about, well, I couldn't, but someone could give a colloquium about how you drive these winds at these tiny scales. But I'll be talking about what these winds do to the galaxy. So for all intents and purposes, I'll just assume that there's some central source that is generating a wind. I'll assume this wind to be roughly 10 to the 4 kilometers per second. That's sort of usually called an ultra-fast outflow. I don't know if it's because you can then form the acronym UFO, or if it's just an accident. UFO.
Yeah, it's a bad accident.
It was a bad accident. So I'll just assume that there's a central source of a wind, and then I'll ask what does this wind do when it propagates into the galaxy. So we can just start with this very easy model where the galaxy is just a slab of homogeneous density. I'll then show you what happens in a more realistic case. If you look at just the speed, you'll probably realize that unless the gas is 10 to the 10 Kelvin, this is going to be highly supersonic wind. So what it's going to do is that it's going to drive a very strong shock wave through the galaxy. That's shown there with this second line. That's the forward shock. It just sort of pushes the gas in the galaxy outward, and it accelerates the gas in what may potentially evolve into a galactic outflow. But actually, as you sweep up gas, the shell of swept up interstellar gas will slow down. So it initially may be driven at 10 to the 4 kilometers per second, but as its mass increases, just by momentum conservation, is going to start slowing down. So this means that the very fast wind is now driving into something that is pushing against it. And what then happens is that you get a second shock. This is the shock that happens because the gas is pushing into the wind. It's called the reverse shock. And what it does is it converts the kinetic energy of the wind into thermal energy. So in other words, what this does is it generates a very hot bubble with a temperature of 10 to the 10 Kelvin. And then if you conserve the energy in this bubble, and I'm not suggesting that energy conservation is something we can kind of play with. What I mean by that is really the radiative cooling is not stealing the energy from this hot bubble. What it will do is that it just expands it adiabatically, a bit like a bomb going off in the center of the galaxy. So it just does PDV work on its environment and drives what is called an energy-driven outflow. We've done, it really is, I think, worth stressing that if you want to really model this kind of phenomena in a galaxy simulation accurately, not just sort of not just qualitatively, you have some hot gas moving, but really, this is really a physical solution. You have to spend years coding. And what we did was I had to come up with a name for that so that people even noticed it. But what we've done was we've developed a new model that I think does this quite well. So the code we use is called AREPO. It discretizes the gas flow into a Voronoi tessellation. So that's actually just the mesh on which you solve the Euler equations. And then what we did was we created that weird thing, which is really just 2 layers of cells that define this very clean boundary. And then what you do is you put a boundary around each of these black holes. You now have a solid angle and a surface boundary. And what you can do is you can set fluxes for mass, momentum, and energy such that they mimic exactly what maybe, for example, people detect at tiny scales for ultra-fast outflows. Or you can also use it to put in what people predict when they run accretion disk simulations, which we don't, which has to do things at scales that we cannot resolve. And I'll show you just a video of such an outflow going off in a homogeneous medium. You really see here the structure I discussed in the previous plot. So you see the freely expanding wind, you see the forward shock and the ambient gas which is being swept up, and then you see this hot bubble which is forming because of this reverse shock. So this model is really reproducing at least qualitatively, the behavior. We've also checked against the analytic solutions that this model is also actually doing this correctly in a quantitative way. So that plot on the right shows you just the radius of the shell as a function of time. And in yellow, you see the simulation predictions, and these curves, sorry, not curves, lines, the dotted line and the dashed line give you what actually you would expect analytic. And you see that there's good agreement between both. So we then, based on such tests, and I also invite you to look at the paper and look at other tests, we now accept that this model is really driving an energy-driven bubble. We can put it in more complicated simulations and make some comments about what energy-driven winds do to galaxy evolution. And I'll just show you some early results. Here is a Milky Way-like galaxy that you see edge on. You see two quantities. This is the density, and basically this is the disk edge on, and that will be the wind mass, which is injected by the black hole. And I will just turn this on now. I stress the wind is actually spherical at small scales, and it has a speed of 10 to the 4 kilometers per second, so it's probably UFO. And what you see is that the wind is, as Andreas also mentioned, collimated by the ambient gas and drives these biconical outflows. They look a bit like the Fermi bubbles, actually, even when you look at the X-ray emission. So, and if you look at it long enough, you also see that it does affect the galaxy in lots of different ways. Some are very obvious. So if you compare this color with the initial color, you see that it's decreasing the density of the gas halo, especially as you have multiple of these episodes, but it's also sending these shock waves through the disk. So it's kind of reducing the density in the central regions of the disk, and also kind of actually increasing the density at larger scales in the disk. As before, we're not blowing up the disk. So we're not kicking out all the disk. That's incredibly difficult to do, even with such a highly energetic wind. So that's again cementing this conclusion that there is certainly an effect of having this AGN, but it may be much more long term than it is short term, even if it's quasar mode. Okay. All right. So just a bit more quantitatively, this just shows you how you go from something which is 10,000 kilometers per second at a few parsec scales, what that develops into at kiloparsec scales. And you see that it drives an incredibly complicated large-scale outflow. This is at a time where it's already reached tens of kiloparsecs, so it's escaped the galaxy completely. And you see all kinds of velocities in these outflows. So there's no clean shell propagating. It's really a big mess, even in a simple system like a disk. And on the right, you see the Saffirmation history. You can see that at the moment the AGN switches off, that's the vertical line. You immediately reduce the Saffirmation rate, but that's actually, we're talking about a factor of 2 or 3. We're not talking about a factor of 100 or 1,000. So again, this is entirely caused by this central reduction in the density. And there's also a decline with time. That would happen naturally because, the gas, it takes time to cool from the halo, but the AGN make this decrease be even steeper. So it's having kind of two effects. One is just a very rapid clear gas out of my way in the center of the galaxy on the scale of a few mega-year. And then there is a sort of giga-year effect of slowly and gradually preventing gas from falling back into the galaxies. And again, all this from a very easy 10,000 kilometers per second wind in the center. So it's really, I think, interesting to compare how simple that is to just how rich and complicated that becomes even in a simple setting, which makes these things actually quite difficult to even constrain, even in a simulation, actually. All right, so that's one model for winds. I also talk about radiation pressure because I know people here are interested in red quasars. So there's a completely different idea of how you drive these powerful outflows, that makes use of the momentum which is carried by the photons released by an AGN. So this momentum can be imparted to the interstellar medium, for example, as the dust grains, which are embedded in the ISM, absorb the UV and optical photons. So when this happens, they get a kick in the radial direction and they may be pushed outwards. If this luminosity is high enough, you can even overcome the gravitational pull and completely blow out the galaxy, or at least analytic models with in spherical symmetry would suggest that could happen. And there are two regimes here. One is called a single scattering. This is because UV and optical photon only collides with a dust grain once. After it does that, it will be re-emitted in infrared, and the infrared photons will just escape the system and not do anything. So in this case, yeah, you have your dusty quasar, it's absorbing all the UV and the optical, it gets one kick and starts maybe moving outwards a little bit, but then the photons come out in the infrared and don't do anything. And then there's actually a second regime, it's called the multi-scattering radiation pressure regime. This happens if you have particularly high column densities, or in other words, the gas is very dense and very compact. And here it's possible that even these re-emitted infrared photons will be absorbed again. And if that's particularly efficient, what then happens is that the infrared photon will have to actually be absorbed and re-emitted multiple times before it has a chance of leaving the galaxy. And if you forget the angular direction, because we have spherical symmetry, we can focus entirely what happens along the radial direction. What a photon does is it kicks outwards many times before it escapes. Of course, there's more volume in large radii, so the radial kick will be preferentially outwards. So what this means is that each photon can now impart this radial momentum more than once. For spherical symmetry, that's actually related to the optical depth in the infrared, but it means that you can, in principle, increase the radiation pressure force that the AGN exerts on its surroundings. This really requires this extreme gas density and small galaxy, though, for it to work. And it also requires the infrared fluid to be effectively trapped by the interstellar medium. You can imagine if there are holes, for example, that the infrared photons just leak through. So we really need to test this with actual cosmological simulations. And that's what I'll present next. So to do this, because we're now dealing with radiation, you cannot run just, or you can, but it's more accurate to run both what's called a radiation hydrodynamic simulation, where now you don't just do the hydro, you also have the radiative transfer for the AGN and stellar radiation, and then the coupled, so the effect of the radiation on the density. So this is, as I mentioned, through radiation pressure, single scattering, multi-scattering, that's really what I'll be talking about. But there's other effects. For example, the UV radiation can ionize the gas, so change the cooling rates. You also heat the gas somewhat. So there's lots of different ways, but really the topic here is this radiation pressure. And what we wanted to know is actually, it's one thing to do a spherical symmetric analytic model and show that it works, but does this work in a sort of realistic galaxy evolution? That's why we ran these simulations. Okay, I'll just show you the results. First result is that single scattering radiation pressure, where the infrared radiation is irrelevant, is not driving outflows at realistic luminosities. So we find, if you look at the blue points, so this plot shows you the speed of outflows as a function of the AGN luminosity. If you look at the blue points, you find the results for single scattering radiation pressure. It does expel gas, but you need to reach luminosities which are a factor of 10 higher than realistic, and we observe at redshift 6 quasars. So in other words, you need more than L/c to start driving such a large scale outflow. And this, for people who are familiar with that, already starts sounding a bit like energy driven, because that's one way to produce more than L/c, or the multi-scattering infrared radiation pressure. So I'll show you now what that does. You may have guessed that I was going to show you the red data points. It actually works. It's the same simulation. It's exactly the same time, the same physics otherwise. The only difference is that we now switch on the infrared opacity from 0 to a realistic value. And what you see now is that you start driving outflows at luminosities which are now realistic and in line with the luminosities we observe at redshift 6. And on the right, this is just showing you the optical depth as seen by the AGN in different directions. You see, once you have these infrared effects, you start clearing out low density channels through which the radiation can escape. Okay, but it is really showing you, if you're looking at red quasars, they may be a very interesting phase because this may be the time at which they are just about to clear out and become a type 1 quasar, for example. And maybe that's also an important part of the feedback loop that we need to explain massive galaxies. So you've seen the outflow, you play there. I did not have to comment. I know that that's what people were looking at. I just show you some details about these outflows, okay. I'll go quickly. So these outflows look very smooth in the video. Actually, when you look at the simulations, they are incredibly complex. So that shows what's called a phase diagram. It shows on the y-axis just the temperature of gas as a function of the radial velocity, and the color shows the density. And so if you take anything above 500 kilometers per second, let's call it an outflow, it's flowing out of the galaxy, and you see that it can be from 100 Kelvin to 10 to the 9 Kelvin. And if you look at the color and see the density, you can see that this is about 5 or 6 orders of magnitude in density. It's actually interesting to make the experiment of not showing the velocity and just showing people the color, and they would think this is just the interstellar medium. It's really just like the SM, but being blown out of the galaxy at incredibly high speeds. If I switch off the quasar, it kind of goes away. So it's definitely the quasar radiation, which is boosting particularly this ionized phase. Maybe why O3 is such a good way of tracing these outflows. Every other phase becomes more important, the cold phase and the hot phase. If I go back and forth a few times. Effect on the star formation rate, like in the energy-driven outflow, there is a suppression in star formation, but this is really maybe a little underwhelming once you take into account that this is 5 times 10 to the 47 x per second. So there is obviously some reduction. You expel gas from the center, but again, gas keeps flowing in. It's very difficult to interrupt the star formation very rapidly. This just shows you, because observers like that, the outflow rate profile for different phases. You see that, cold dominates small scales, and then it's taken over by a warm phase, maybe seen in O3. But then actually at large scales, we really need to look at X-rays to see an outflow according to these simulations. Okay, so the final part of the talk is just going back to a bit more to observations and how we can test both the feedback and the quasar environment I've been discussing. To do this, we looked at about 30 quasars redshift 6 with an instrument called MUSE and tried to identify the radiation coming out in Lyman alpha, which is one of the brightest lines in the universe. And Lyman alpha traces gas at about 10 to the 4 Kelvin. So it traces cool gas, which is already, well, if it's cooled from a hot halo, it will have already done so, but it's essentially tracing the material we think is ultimately feeding the central galaxy and the black holes. And about 12 of these systems showed these extended Lyman alpha nebulae. Of course, we see them at redshift 3 and 4. They can be huge, hundreds or 200 kiloparsecs. Here, the surface brightness limit, we see them, they're about 40, 50 kiloparsecs in size, and they display quite a range of morphology. So the red circle shows you where the quasar is located, and the contour gives you the 10 to the minus 18, I think, roughly sensitivity, below which we are able to identify this extended emission. And here is a quasar is centered on the emission. On the right, you see that it's even looking like it's coming outside of the nebula. So what is going on? And can actually the simulations I've shown you, where we claim that we explain the rapid assembly of massive black holes, can those same simulations be now finally put to a test? And would they give you anything like this if you post-process them for Lyman alpha radiation? So I've done exactly that. So I've taken my radiation hydro cosmological simulations, the ones that were designed to actually test AGN feedback. They were not designed at all to do CGM studies. I was not interested in that actually before. So this is really a coincidence. It started with someone asking me for a proposal, pick the picture for a proposal. So with this code, we use a public code called RASCAS that does Lyman alpha rate transfer. And we tested a wide variety of emission scenarios. I don't have time to explain, but Lyman alpha can be produced in different ways. One is if you photoionize hydrogen and then the gas de-excites and you get Lyman alpha. Another way is if you generate the transition not via photoionization, but via collisions with free electrons. So here it's collisional excitation. And then there's this mechanism I'll be discussing in a second. BLR stands for broad-line region. So it has something to do with bouncing photons all the way from the AGN to halo scales. Okay, so I'll just show you very quickly. You have to do radiative transfer because Lyman alpha is complicated. In very simple words, it's absorbed very easily by neutral hydrogen. So that means that if you see a Lyman alpha photon coming out of there, it could actually have been produced there because it's bounced around off all the neutral hydrogen in between. So to really interpret this line and to even model it, you have to do radiative transfer. The spectrum, it could be a nice delta function center at the line center. It goes through some homogeneous slab of neutral hydrogen and it can come out as a double peaked shape. If this gas is moving, even worse, you get shifts to the left or to the blue or to the red. So you really have to do that numerically. And just one thing before I show you the results. I mentioned the scattering was important. I gave a silly example. In this case, what could happen, and this is just an extreme case scenario, is that you could imagine that there's a very bright Lyman alpha source positioned at the quasar. We actually know this happens from observations. There are bright, broad Lyman alpha lines in quasars. It's actually possible then, just in theory, that these photons scatter off all the neutral hydrogen in the halo. Some of them come to our line of sight and then make it look like there's a huge bubble of Lyman alpha on large scales. That's what I call broad line region scattering. And it's being argued against strongly because when the photons scatter, they also shifted in frequency to blue or to the red. And when you shift things in frequency, the cross section goes down. So if you do this too efficiently in the center of the galaxy, so the photons are sort of bouncing and trapped in the center of the galaxy, they can pick up such extreme frequency shifts that then they just go out of the galaxy and they don't do anything else. They don't interact with the cold gas or the neutral gas in the halo that is necessary to reflect these photons in our direction. So this is the reason why this mechanism is being argued against in the past. So, okay, results, and then we're done. We've seen these pictures. You see the filaments, the satellites. This is the quasar host disk. You see face on. There's a hole in the center because the radiation pressure has cleared out the galactic nucleus. And then I'll just translate that into Lyman alpha surface brightness. We smooth these to imitate the resolution of Muse and to get as close as possible to the observations I've shown you. So first point is we do get some extended emission in Lyman alpha. The yellow contour corresponds roughly to the sensitivity of the Muse observations I've shown. So it is extended on scales of about 6 arcsecond, depending on how you measure that. That's roughly 30 to 40 kiloparsecs indeed. Okay. These nebulae look completely different depending on which direction you look at them. This is actually always the same system. You're just looking at it from a different random direction. And you can see that just like in the observations, we get a range of morphologies. So for example, number 5 in the center at bottom, you see a nebula where the quasar is centered on the surface brightness peak. If you look at number 3 or 4, you see a case where the quasar, which is the red cross, almost looks like it's coming out of the outside of the observable part of the Lyman alpha nebula, which is the yellow contour. So this diversity seems to come out in the simulations as well. It's crazy, I thought, because we, as I mentioned, did not tune these simulations in any way for that. Okay, so how about the surface brightness profile? So this is something observers do. So they put shells and then they measure how the surface brightness profile scales with radius. That's what the observations suggest at redshift 6, the median and some kind of uncertainty, 25th to 75th percentile range. And here are the simulations. So the blue dashed curves are just different lines of sight. The black curve is the mean of these different lines of sight. And this was crazy and horrible because I thought if any error is present, then this goes away. It's worse than getting things wrong because you then can find ways of making them right. So if this works like that, then you cannot have an error. But it seems to, as far as you can tell, be free from errors. Again, just to show you these different lines of sight, I just have something to do with the different orientations of the host galaxy. So it may be interesting to actually try to map these Lyman alpha nebulae and see if they tell us something about the orientation and the morphology of the galaxy that is hosting the quasar. Already redshift 6. It's cool that we might be able to do that. And 2 minutes, yeah. And then just the last point. What is actually, I mentioned the different mechanisms, recombination, collision excitation, and broadline region scattering. So which one works? Well, they all work, but it seems there's two models that are sort of favored. If you only have collision excitation, for example, it doesn't do a great job at recovering neither the normalization nor the shape. But if you combine it with recombination radiation, you get one of the blue lines, the lighter blue one, and this seems to get close to the observations much better. But if you look at the green shaded region, that gives you the contribution of just having a point source in the center of the galaxy and nothing else. There's a range because this normalization depends on how much of the AGN luminosity comes out in Lyman alpha. So these are just some plausible values. But you see that for some of the parameter space, you may even be able to explain the nebulae entirely just by reflecting Lyman alpha photons from the nucleus all the way to 50 to 100 kilopascal scales. So I said that this works. The people have argued against this model before, but now I'm telling you that it actually works. So here's an image of the nebula that we get with this broadline region scattering. This is now a standard simulations AGN feedback. I'll show you what it looks like if we switch off AGN feedback. And by the way, AGN feedback was not modeled in the simulations used in 2014 to discredit this scenario. And this happens. So it goes away. And indeed, if you don't model AGN, you don't get these extended Lyman alpha nebulae. Why? Well, there's first of all too much dust, which absorbs the Lyman alpha photons, and there's also too much H1, which means that the red shifts and blue shifts are too crazy. It's actually a velocity of 1500 kilometers per second shift. But if you have the AGN, you destroy the H1, clear out the dust, and the photons can escape and bounce off the neutral gas in the halo. Last thing before I show you just the conclusions. So I'll be moving to the UK, and we are looking for a postdoc who's interested in running these kind of simulations I've shown you. We really want to compare these simulations one-to-one with observations. So if you find this interesting, you can either contact me or Chris if you know him, and I will leave you just with my summary.
Very nice. So let's start with.
Got a question about this nebula. Did you try to compare the kinematic with observed nebulas? I lost expression or something.
I should have put the spectra. So we have looked at the, so we produced data